In this next section, we are going to talk about finding extreme values of our partial derivatives. So if you think back to our two variable functions, so f of x equaling y, we said that given that type of function, if I looked at the graph and we found kind of a high point there, that was our relative max, and the low point was considered our relative min. Well, once we start adding variables to this, and for these functions I'm going to preface this by saying we are only going to be looking at functions of three variables, in the sense z is equal to an f of x, y. We are not going to do f of x, y, z's, f of x, y, z's, w's. It's just going to be z equaling f of x, y, because these are the ones we can actually think of pictorially. Okay? So if I'm given a function z equal to f of x, y, then I still have my two cases for the relative max and relative min. The relative max just says that when I look at the partial derivatives, in both directions it's going to be a maximum. Okay? Or, if I'm looking for relative min, in both directions it's a minimum value. Okay? But once we start adding in that other variable and we start looking at more than one direction, we have a third case, and that's what we call a saddle point, where in one direction it's a minimum, and then in the other direction it's going to be a maximum. And so it almost looks like a saddle, right? I can sit somebody on this and think of, there's my little stick figure sitting on the saddle, and I can actually see that in one direction, in this case in my x direction it's a maximum, in my y direction it's a minimum. Okay? And so we're going to talk about how to find these points given particular functions. And so before I do these examples, you will see some examples in the book that go back to a numeric method, where you're looking at a table and you're trying to find these points. And the idea there is to think of it in terms of these things. If I'm looking at the rows or columns, in order for it to be a max, it's got to be the biggest value in that row and in that column. Or if I'm looking at a min, it has to be the smallest value in both the row and column. Your saddle points are going to be a little harder to find because you have to look at the rows and columns separately, and in one case it has to be a maximum value, and the other case it has to be a minimum. And it can change which direction that is. Okay, it's not always going to be in the x or in the y. It's going to change back and forth. Okay, so you're going to have a couple of problems like that, both in WebAssign and out of the textbook, that you're going to want to look at and just see if you can actually find the maxes and mins and the saddle points based on the tables. Okay? Most of your problems are going to be very similar to what we did back when we had y equals f of x. And so if you recall, we had this second derivative test. And recall, this is not the only way we did it back then. But the reason I picked the second derivative test is because we're going to do something very similar with the multivariable case. Okay? So using the second derivative test, it said if I can find a critical value, meaning I take my function, I get the derivative, I set that derivative equal to 0, and I find those x values. And we called them x naught. So if x naught was a critical value, then we said using the second derivative, whether it was positive or negative, basically told us whether it was a max or min. So if it was positive, then we were looking at upward concavity, and we were looking at a minimum value. And if we were looking at f double prime being negative, then we were looking at downward concavity and looking at a maximum value. Okay? For a two-variable function, let's say z equaling f of x, y, we're going to start doing the same thing. The first thing we need to do is find the critical points. In order to do that, notice here we have to have an x naught and a y naught, not just an x naught, because now we have two variables in our function. And so to get these points, we're going to solve a first order system, meaning we're going to find f sub x, the partial with respect to x, and the partial with respect to y, set both of those equal to 0 and solve the system. So whatever values we get have to work in both partial derivatives in order to be a solution or a critical point of our function. Okay? Then what we're going to do is we're going to use what we call the Hessian. The Hessian is our second derivative that's going to tell us about what the critical points are doing. And like I said, this is a little bit more involved than just finding the second derivative of a one-variable function, because now we have to take into account the different directions that we're looking at. So our Hessian looks at the second derivative of x, the second derivative of y, and the mixed order partial derivatives. Okay, so notice these are all second order derivatives. In this case, both are x, both are y. Here we do x, y, and then yx. And all of these are going to be evaluated at the critical point. So we'll take fxx times fyy and subtract off the product of the mixed partials. And this will tell us what is happening to the extreme values. Okay, so basically for h, we're going to get two things. Well, we could get three, but I'm going to talk about the main two first. We could get that our h is positive, or we could get that h is negative. And like I said, there's that third case where h is 0, and I'll talk about that last. If our h turns out to be positive, what that's saying is that these partials here are bigger than the mixed partials, and more importantly, that these have to have the same sign. In other words, this has to turn out to be positive and bigger than this number here. And if these have the same sign, then I'm looking at one of these two cases, right? That means that both my x and the y direction are doing the same thing, okay? If those are positive, and my x, my second order partial with respect to x, is also positive, then both the x and y are concave up, and so I'm going to be looking at a relative min. Okay? If h is positive, so again they're going the same direction, and fxx is negative, then what this says is that both of them are concave down. So x and y are both concave down, and I'm looking at a relative max. If h is negative, then that means these two things have to have opposite signs, so that when I subtract, this whole term comes out negative. Okay? If these have opposite signs, then that tells me one is going to be a maximum and one is going to be a minimum. And so then I get a saddle point. Okay? And then there's that third case. So if my h is equal to 0, well, then my test is inconclusive, because that tells me either these have exactly the same value, and so I can't really tell whether my fxx and fyy are the same or different, because it completely cancels with my mixed order partials. And so here it's inconclusive, and you'll need to find some other method to classify the extrema. And usually this can be done easily by plugging in some values or looking at what the graph looks like. And for these will be fairly nice graphs that you'll be able to get a picture of. So let's look at an example or two of how to find our extreme values for a multivariable function. Okay. So first, let's quickly review the steps. So here, if I want to find the extreme values, the first thing I'm going to do is find my first order partials, so f sub x and f sub y. Then I want to solve the system to get my critical values. So I'm going to set each of those equal to 0 and solve the system. And again, I stress that solve the system. It's not solving them each individually. Some of your problems, it may work out that way because I've only got one variable in each equation, but you really are solving so it works in both equations in the system. Okay? Then I want to go ahead and find my second order partials. So I'm going to take the partial derivative of each of these and then apply the partials again. Okay? Once I have those second order partials, I want to evaluate them at their critical point. So this critical point we found in 2, I'm going to plug it in to all of these partial derivatives and get those values. Then I want to find my Hessian. So I'm going to take that second order partial with respect to x, multiply it by the second order partial with respect to y, and then subtract the product of the mixed partials. Okay? And then I can state my solution. So once I have that Hessian for each critical point, then I can figure out what's going to happen, whether it's max, a min, or a saddle, or if I need some more information. Okay? So let's look at this example. F of xy is equal to x cubed plus y cubed minus xy. Okay, so the first thing I want to do is I want to find my first order partials. So I want to find f sub x and f sub y. So again, f sub x, we can see is 3x squared. That term's going to go to 0 minus y. And f sub y we can see is going to be 3y squared minus x. Okay. From there, I want to solve the system. So I want to set up 3x squared minus y equaling 0 and 3y squared minus x equaling 0. Now to solve this system, there's a number of ways you can do it. You can use your substitution or elimination. So recall that from your pre-calc class. In this case, it's probably going to be easiest to do some sort of substitution. So if I use this last equation, x will equal 3y squared, I can plug that into the first equation. So I can see 9y, that's wrong, 27 y to the fourth minus y is equal to 0. I can factor out a y. So y will equal 0, or 27y cubed equals 1. So y cubed will equal 1/27th, or y cubed, so y will equal a third. Okay? Once I have those y values, again I need to plug back in and get the corresponding x values. Okay? And so I can see here if y equals 0, x is going to equal 0. And here, if y equals a third, we can see I'm going to get a ninth times 3, which is a third, so x will equal a third. Okay? So there's my two critical values. Okay. From there, now that I have my critical values, I need to find my second order partials. Okay? And so I'm going to take my fxx and fyy that we just found and find the mixed order partials. So fxx means I'm taking the derivative of this with respect to x. So that's just going to be a 6x. That term is going to go to 0. Fyy says I'm taking the derivative of this with respect to y, which just looks like 6y. Fxy says I'm taking the derivative of this with respect to y. That goes to 0, so that's just going to be -1. And fyx says I'm taking the derivative of this with respect to x, which again is just -1. Okay. Now I want to find all of these at the critical values. Okay. So fxx at 0, 0. I'm going to start with that first critical point. We can see is just 0. Fyy at 0, 0 is also going to be 0. Fxy at 0, 0 is -1. And fyx at 0, 0 is also -1. Okay? Now I'm going to use the other critical point and do the same thing. So fxx at 1/3, 1/3. Plugging 1/3 in there looks like 2. Fyy at 1/3, 1/3 is also going to be 2. Notice for the mixed order partials, I'm still going to get -1. Okay, so now that I have all of these, I want to find the Hessian for each of the critical values. So for 5, I'm going to find h at 0, 0, which says I'm going to take fxx times fyy minus fxy times fyx. Okay? And so here we can see 0 minus 1. This is going to be a -1. Okay? And h at 1/3, 1/3, I can see is going to be 2 for fxx times fyy, which is also 2, minus a -1 times a -1, so times my mixed partials. So here we're going to get 4 minus 1, which looks like 3. So to state my solution, now that I know the values of h and I know the corresponding values here, I can go ahead and state my solution. So 0, 0, because h was negative, that tells me this is a saddle point. And for 1/3, 1/3, h was positive. So now I have to go back to my fxx. I can see that for 1/3, 1/3 was also positive. So positive and positive means everything was concave up. So this is a relative min. Okay? And so there's an example of what it's going to look like for you to find your second order partials using your Hessian. Okay, so in this next example, we are going to look at f of xy equaling x squared plus 3y squared plus 4x minus 9y plus 3. And we want to find the extrema and classify them, so tell what type they are. Okay, so again, the first thing I want to do is I want to find the first order partials. So I'm going to find f sub x, and I'm going to find f sub y. So again, for f sub x, treat everything that's not x like a constant. So we'll get a 2x plus 4, and everything else goes to 0. And then for f sub y, we can see we'll get a 6y minus 9, and everything else goes to 0. Okay? So the second thing we're going to do is we want to find the critical points. So again, I want to set up the system 2x plus 4, 6y minus 9, both of these equal to 0 and solve. Okay? So this is one of those examples I was saying sometimes you're going to get some that are actually distinct from each other, and I can actually solve them individually to get my critical point. Okay? And so here I can easily see that x has to equal -2, and y is going to have to equal 3/2. Okay? So there's my critical point. And in this case, I just have the 1. Okay? Now that I have my critical point, I can go ahead and find my second order partials. So fxx, fyy, fxy, and fyx. Okay? So here, taking the derivative with respect to x, we see we get 2. Here, taking the derivative with respect to y, I see I'm going to get 6. Here, taking the derivative with respect to y, I get 0. And for this one, with respect to x, I get 0. Okay. Fourth step is that I'm going to evaluate my second order partials at my critical value. Okay. And so here we can see fxx at -2 3/2 is going to be 2. fyy at -2 3/2 is going to be 6. My mixed order partials are both going to be 0. Okay. So now looking at my Hessian, h at my critical value is going to be my fxx times my fyy minus my mixed partials multiplied together. And so here we can see that's 12. That is definitely greater than 0. So this being positive and this being positive gives me my solution, which says that -2, 3/2 is a relative min. In this last example, we're going to do the same thing, just a slightly different function. Okay, so here again, given my f of xy there, I want to start by getting my first order partials. So my f sub x, in this case, notice I've got some grouping symbols here, so you got to be a little careful. Here I'm looking at basically a 1/3 x cubed, so the derivative is just going to be x squared. The 1/3 times 8y cubed, no x's in there, so that goes to 0, minus 4x, that's going to go to 0, and that's going to go to 0. For f sub y, same thing. If I look, I'm basically looking at an 8/3 y cubed, which is going to be 8y squared. Over here, minus the 2y squared, which looks like minus 4y. And again, that constant just goes to 0. From there, I need to solve my system. So x squared minus 4x equaling 0. 8y squared minus 4y equaling 0. Here I can see, again, they're independent of each other, but this one's not quite as nice because I have squared terms in there. So when x squared minus 4x equals 0, I can pull out and see x will equal 0 or x will equal 4. And then here, 8y squared minus 4y equaling 0, I can pull out a 4y, and I see that y will equal 0 or y will equal a half. Okay. Now here you have to be a little careful because for each of these x's, they will satisfy both equations, and same thing for each of the y's. So here, excuse me, my critical values, I actually have 4 of them. I'm going to have 0, 0, 0, 1/2, 4, 0, and 4, 1/2. Okay. So now I need my second order partials. So my f(x)(x), again, taking the derivative of that f sub x with respect to x, we'll get 2x minus 4. F(y)(y), we can see taking the derivative there, we'll get a 16y minus 4. F(xy), I'm going to get a 0, and F(y)(x), again, I'm going to get 0. Okay. Now, evaluating these at each of the critical values. Okay. So this one, instead of writing them all out, I'm just going to do it this way. So at 0, 0, we can see that f(x)(x) is going to be negative 4. F(y)(y) is going to be negative 4. F(xy) is still 0. F(y)(x) is still 0. At 0, 1/2, notice the only thing that's going to change are the ones that have a y in it, because the x value is exactly the same. So f(x)(x) is still going to be negative 4, f(xy) and f(y)(x) are still going to be 0, but now f(y)(y), plugging in there, when I put in a half, I'm going to get 8 minus 4. It's going to give me a positive 4. Okay. At 4, 0, this one's going to be very similar to the 0, 0. The only difference is the ones that have an x. So my f(x)(x) is going to equal, plugging in 4, we get 8 minus 4. That one's going to become positive. f(y)(y) will be a negative 4. And again, f(xy) and f(y)(x) are both going to be 0. And then lastly, at 4, 1/2, both the xx and yy will change. So xx will be positive 4, fyy will be positive 4. The fxy and fyx are still both 0. Okay. So now to find my Hessian at each of these. So I'm going to have 4 of these. So at 0, 0, I've got -4 times -4 minus 0 times 0, which looks like 16. So this one is positive, and the sign here is negative. So both are concave down, so this will give a max. At 0, 1/2, we're looking at -4 times 4 minus 0, which is going to give us a -16. Negative Hessian means a saddle. At 4, 0, I've got 4 times a -4 minus the 0. So again, a -16. And at 4, 1/2, we have 4 times 4 minus 0, which is 16. This is positive, and the F's are positive, so this is going to be a relative min. Okay. And so to state this, we will say F has relative max at 0, 0. It's got a relative min at 4, 1/2, and has saddle points at 0, 1/2 and 4, 0. All right, so there is our last example of our second derivative test for multivariable functions.